Hello class. You guys have been doing a great job when you've been working on simplifying, multiplying, adding, subtracting, dividing our rational expressions. Even with those complex rational expressions, you did a very good job. And so now we're going to introduce graphing. We're not going to jump all in. There's a lot of characteristics of graphing that we want to cover. So today we're just going to look at finding the domain, the vertical asymptotes, and the holes. We'll do 3 lessons and then we'll kind of put it all together. So here we go. When we were working with quadratics and other polynomial functions, our domain was always all real numbers. And we're going to continue to assume that whatever we're given is all real numbers unless we find an exception. Now, an exception is going to be when we're working with rational functions. It's going to be when b of x is equal to 0, because notice that b of x right here is in the denominator. We cannot divide by 0. So b of x cannot be 0. So to find our exclusions, we'll say b of x, whatever that is not equal to 0, and that will give us our restriction. Let's show you some examples. So let's find the domain of a few functions here. On this function, we have f of x is equal to x squared minus 25 over x minus 5. Now we do have that we could factor this top part and find factors that cancel out, but when we're finding the domain, we want to do it before simplifying. And when we are looking at the domain, we don't care what the numerator is. I don't care. Now, I don't know, I don't care. So we're just looking at that denominator, and we're going to say that that denominator cannot equal 0. So if I add 5 to this inequality, I have x cannot equal 5. That is our restriction. If you put it in interval notation, remember interval notation of real numbers is from negative infinity to infinity. Well, we're going to do that same thing, negative infinity to infinity, but then we're going to include our interruption. This is our exception, because it's all real numbers except for 5. So it's going to be all real number, negative infinity to 5, and then we're going to have a little break, and then we're going to, at 5, pick it up and go to infinity. So there's our domain for this function. Once again, we're just going to be looking at the denominator. So we're going to say that x squared minus 25 cannot equal 0. Well, this x squared minus 25 can be factored. So we have factors of conjugates, x plus 5 and x minus 5 cannot equal 0. So we have to include that neither of these factors can equal 0. So x cannot equal negative 5 or 5. And so in interval notation, we're going to go from negative infinity to infinity and just exclude our exceptions, negative 5, and then from negative 5 to 5, and then from 5 to infinity. So that's our domain. And one more here, we're going to take a look at this denominator, x squared plus 25. We're going to say that x squared plus 25 cannot equal 0. Well, this is prime and does not factor, but let's just use the square root property and see what happens. So I'm going to subtract 25 from each side, and I get x squared cannot equal negative 25. So then we'll take the square root of each side, and we get x cannot equal positive or negative 5i. Well, this is an imaginary number, and our domain is just the listing of all real numbers. So our domain, what we can graph on the x-axis, is still all real numbers. So there are no exclusions on the real number line. So our domain is negative infinity to infinity. So when we're looking at exclusions of the domain, it begs the question, hey, what's happening? What's going on right there? Well, there's two things that could be happening. The first thing that could happen is that it could be a hole. A hole where there's just no value at it. And that's when we see that, we would have, notice at f of a, we have a hole. And so it does not exist. And there's just, there's nothing happening there. That's why we draw it as an open circle there as a hole. So, and when does that happen? Well, if we have a factor x plus a, and it factors out in the top, and there's a factor of that in the numerator and the denominator, it factors out. That means we're going to have a hole there. Now, the other thing that could happen is that we could have a vertical asymptote. Which we do at b. So at this one we have a vertical asymptote at x equals b. And that is if x minus b remains after simplifying, in the denominator, that is. So let's take a look at some limits here. We've got this statement here that says as x approaches negative a, and this little piece means from the left. So if I'm coming from the left and I'm approaching a, it looks like I'm coming close to c. And as I approach negative a from the right, it's also approaching c. Let's take a look at the b then. As x approaches b from the left, so I'm coming down here, it looks like it's going towards negative infinity. And as I approach b from the right, it's going up, so it's approaching infinity. We will be asking you for these types of limits or behaviors. Since there's two things that can happen at the exception of the domain, we should really try to find out how we're going to find whether it's a hole or a vertical asymptote. So once we've determined that there are some exceptions, we're going to factor everything in the numerator and the denominator. Any common factors in a of x and b of x create holes. After you've simplified, if there's factors left in the denominator, after simplification, then those create the vertical asymptotes. And one other thing I want to just say, when we have a hole, you're going to, if f of, let's say that it's a, gives us, well, I'll show you on the examples. All right, so we're going to factor this x over x plus 1, x minus 1. So x cannot equal -1 or 1. That's our domain restrictions. We want to know what's happening at that. Now, I have nothing I can factor out. So if it doesn't factor out, it's not a whole. So if these are my exceptions, then at x equals -1 and at x equals 1, these are my vertical asymptotes. And when we get to drawing these, they will be dashed vertical lines on the graph. Let's go ahead and factor this one now. X minus 1 is in the numerator, and in the denominator that factors to x plus 1 and x minus 1. And so we still have the same exceptions, that x cannot equal -1 or 1. But we can cancel the x minus 1's out. So there's going to be a whole at x equals 1. And the simplified version of this function then is g of x is equal to 1 over x plus 1. Now we're going to find, using the simplified version, what g of 1 is. So that's 1 over 1 plus 1, or 1/2. So the whole is at x equals 1, and g of 1 is equal to 1/2, or the ordered pair of 1, 1/2. That whole will be graphed as a circle at this point. Now we still have a restriction here. X plus 1 is still in the denominator, so x still cannot equal -1, so we have a vertical asymptote at x equals -1. So we have a vertical asymptote, and we have a whole at 1, 1/2. So now we get to h of x is equal to x minus 1 over x squared plus 1. And I said to factor all this, but x minus 1 is prime. X squared plus 1 is also prime. So my domain restrictions, x squared plus 1 cannot equal 0. Well, if you do that square root property again, you square that, or square root that. Oops, square root. You end up with not real numbers. So there are no restrictions on the domain. If there are no restrictions, then there are no holes and no vertical asymptotes. And if that's what you're trying to find, you would be done.